Hi, and welcome to the presentation of this poster. The title of this poster is Influence of Thermal Annealing on Nanocrystalline Phase-like Emission and Morphology of Praseodymium-doped silicon-rich hafnium oxide films prepared by radiofrequency magnetron sputtering. The effect of thermal annealing on crystalline phases, like emission and morphology in hafnium oxide Praseodymium silicon-rich films was investigated using various analytical techniques, including scanning electron microscopy, photoluminescence, energy dispersive X-ray diffraction spectroscopy, and X-ray diffraction. The hafnium oxide praseodymium silicon-rich films were deposited on silicon substrate using pure argon plasma and radiofrequency magnetron sputtering. The thermal annealing was carried out in a horizontal furnace with nitrogen flow in the temperature range of thermal annealing equal to 800 Celsius degrees and 1000 Celsius degrees for 15 minutes. The photoluminescence study revealed a worth of photoluminescence band in the visible spectral range, which was associated with the emission of host defects and praseodymium ions due to transition in the 4F inner shell. The relative contribution of each emission depends on the crystal phase of the host matrix and thermal annealing. The scanning electron microscopy study showed the grain structure with average size of 20 to 15 nanometers, which tend to increase with thermal annealing and film densification. Furthermore, X-ray diffraction analysis indicate the presence of tetragonal hafnium oxide and silicon oxide phases after thermal treatment at 1000 Celsius degrees and 1100 Celsius degrees. The peculiarities of photoluminescence include thermodification with crystalline phase transformation and their dependency on temperature of thermal annealings are analyzed and discussed. Surface morphology. Sample morphology is given by the structural zone model. This model indicated that the final structure of film is given by three main processes. Shadowing, in which phenomena such as geometric interaction of the deposited atoms and the surface are included, low temperatures of the substrate. Second, surface diffusion, mobility of the atom of surface and at the interfaces, grain boundaries at average substrate temperatures. Third, bulk diffusion, mobility of atoms in volume grains. And fourth, recrystallization, phase transformation, change in crystal structure at high substrate temperatures. Activation energies for diffusion are related to melting temperature. The process depends on the substrate temperature melting temperature range. The samples were grown at temperature of 400 Celsius degrees, which is considered as the temperature of the substrate. In addition, the compound that had the greatest contribution in sputtering was hafnium oxide, whose melting temperature is 2810 Celsius degrees. Therefore, the substrate temperature melting temperature ratio is considered 0.14. There is a zone called T, zone where plasma pressure is also involved. This zone is considered for substrate temperature melting temperature ratios. Between 0.1 and 0.2, this zone is characterized by the formation of grain dense arrays separated by grain boundaries. That's why the surface shows the presence of grains of different heights. The high annealing temperature results in increase the grain size in the films, and it's caused by the change in grain boundaries and coalescence of small grains. Chemical composition. The results obtained by ADS showed a change in the oxygen peak in a non-monotonic way, which can be attributed to the phase change that occurs with respect to the annealing temperature and the appearance of defects. due to the diffusion of oxygen in the films. The decrease in the amount of oxygen at 1000 and 100 Celsius sample is the consequence of an increase of the number of defects. X-ray diffraction. By means of the X-ray diffraction technique, a very similar behavior of the spectra was observed in the as deposit 800 and 900 Celsius degree samples. In this, peaks belonging to tetragonal hafnium silicates, peak 7, 8, 12, and 13, as well as silicate of tetragonal praseodymium, peak 6, 9, 10. Likewise, a very intense peak can be observed, identified by the number 11, which is attributed to the silicon substrate. It is noteworthy that hafnium and praseodymium silicates appear in these samples due to the high deposition temperature to which the films were subject. For the samples annealed at 1000 and 1100 Celsius degrees, there is a very notable change. The silicate signal disappears, and peaks related to tetragonal hafnium oxide, peaks 2, 4, 6, 9, and 14, and tetragonal silicon oxide, peaks 9 and 11b. The appearance of silicon oxide explains why the emission of photoluminescent decreases at 1100 Celsius degrees. Photoluminescence visible. As you can see, an additional spectrum is observed in the spectrum of the samples annealed at 800 Celsius degrees. This spectrum corresponds to the measurement of a thin film sample of hafnium oxide silicon-rich thin film, but without doping. What is observed is very similar behavior between the sample without doping and the as deposit sample, and the samples annealed at 800 and 900 Celsius degrees, which indicates that these three samples have photoluminescence emission due only to hafnium matrix defects. However, for the samples annealed at 1000 and 1100 Celsius degrees, a change in the intensity and shape of the spectra is shown, which indicates that an emission due to praseodymium is observed. The increase of defects at 1100 Celsius degrees previously described in EDS is the reason why one can see a slight increase of the emission in photoluminescent spectra at room temperature. Photoluminescent infrared. In a similar way, the results obtained of infrared spectral range shows an emission out to praseodymium ions. These emission bands are related to 4F level transitions. As one can see, this effect is observed at 1000 Celsius degrees and is connected to the of high-quality tetragonal hafnium oxide matrix. The above coincides with the observed in the visible range spectrum. Low temperature photoluminescence spectrum, 1000 degrees. Photoluminescence measurements were made for the samples with the maximum emission intensity, 1000 Celsius degrees, in a range between 10 and 300 kelvins to observe the behavior of the emission bands, and observe if the presence of the effects in photoluminescence spectra existed. In conclusion, the effect of annealing temperature in a range from 800 Celsius to 1100 Celsius degrees on the structural properties, chemical composition, and live emission of silicon-rich nanocrystalline hafnium oxide praseodymium thin films has been investigated. The ground sizes obtained by SEM shows a size increment as the annealing temperature increases, according to the structural zone model with maximum size of 50 nanometers. The results obtained by EDS show a non-monotonic change in the amount of oxygen present in the samples, and a decrease of the oxygen quantity at temperature of 1100 Celsius. This decrease relates to the increase of the quantity of the effects and by consequence an increment of photoluminescence intensity, as one can see in the photoluminescence spectra for both the infrared range and visible range. Annealing temperature stimulates the phase transformation from hafnium silicates and praseodymium silicates to the formation of the trigonal hafnium oxide in the samples. This effect can be observed in the change of shapes between the samples temperature 900 Celsius and temperature 1000 Celsius, analyzed in X-ray diffraction, which is related to an increase in the emission of photoluminescence as well as the appearance of the trigonal silicon oxide in the samples. Temperature 1000 Celsius and temperature 1100 Celsius. Studies performed on non-doped samples of hafnium oxide show a similar shape to the as deposit 800 and 900 Celsius spectra in visible photoluminescence, indicating that the emission of these three samples is broadly connected with the emission of the host effects of hafnium oxide. Hi, and welcome to the presentation of this poster.